Last time we got introduced to the idea of pipelining through an example where we basically divided the program into tasks, which is one task is basically one iteration of the outer loop, and then each task had multiple stages. Each stage is basically one iteration of the inner loop, and then we would basically pipeline such that each processor is specialized for one particular stage to potentially exploit the spatial locality available in the program. However, this is not free. Pipelining requires order n synchronization. However, this synchronization is a loose form of synchronization in the sense that it's only a one-way kind of synchronization. For example, the first thread basically keeps signaling the second thread. The second thread keeps signaling the third thread, and so on. So it's like a wave front of computation. Let's look at another example to understand pipelining in a bit more detail. And this example is the successive over relaxation example, or also called the SOR, or I'm going to call it the SOR example. This example is actually a practical real world example, and so it is even more relevant. What is the example? It's a loop nest of depth 2. Recall that pipelining requires a loop nest of at least depth 2, and for I equals 0 to m, I++, for j equals 0 to n, j++, xj plus 1 equals xj plus xj plus 1 plus xj plus 2 divided by 3. In other words, it's somewhat like the blurring function in image processing, where you basically just relax the value xj plus 1 using its neighbors, which are xj and xj plus 2, and itself as well, and just kind of taking the average of them. The inner loop basically traverses over x once. X is a unidimensional array, and then the outer loop basically repeats this for m iterations to relax as many times as possible. Alright, so you basically, the n is basically proportional to the size of x, and m is basically proportional to the amount of relaxation that you require in your logic. Now, this is my program, and the question is, what are my parallelization or pipelining schemes? Now, I'm going to figure out what are the space partitioning constraints or what are the data dependencies, and based on that I'm going to figure out whether this loop can be parallelized or whether this loop can be pipelined. Okay, so and I'm going to do this pictorially. I mean, we could have done the same thing using equations and math, but because it's a two-dimensional loop and it's much easier to understand it using pictures, I'm going to do it using pictorial graphs. So let's say the inner loop is basically the x-axis, which is j, and the outer loop is the y-axis, which is I. And these are the iteration points, 0, 0, 0, 1, 0, 2, 0, 3 for I, j, and so on. Similarly, 1, 0, 1, 1, 1, 2, 1, 3, and so on, 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, and so on. And of course, the iteration order is ascending lexicographic, which means it's a row, I first look at the 0th row, then the first row, then the second row, and so on. Okay, now let's look at the data dependencies. So the first thing here is that there are data dependencies from the I, jth iteration to I, j plus 1th iteration, because at the I, jth iteration, I'm writing to the element xj plus 1, and at I, j plus 1th iteration, I'm reading from j plus 1th element of x. And so I have read after write dependencies of this type, which are just from I, j to I, j plus 1 for all values of I. So I basically get these green dependency edges, which are just these horizontal chains of dependencies, and these are coming from these two axes, xj and xj plus 1. Now there are more dependencies. What are the other dependencies? Well, if I look at dependencies across different iterations of I, at I equals 0, so at 0, 0 and 1, 0, notice that 0, 0 and 1, 0 are both going to write to x1. And so there is a write after write dependency on between 0, 0 and 1, 0. Similarly, there is a write after write dependency from 1, 0 to 2, 0. In other words, I cannot execute the 1, 0th iteration before the 0, 0th iteration. Now, I mean, you may say, oh, it's a commutative operation, but once again, these plus and equality and assignments are basically placeholders for more complicated expressions which may not be commutative or associative. Alright, so basically the 1, 0th iteration cannot be executed before 0, 0th iteration, because they both involved in writing to the same data element, and so there is a write after write dependency. In fact, there are more dependencies. For example, xj plus 1 is being written in 0, 0 and xj plus 1 is being read in 1, 0. So there is a read after write dependency as well. Moreover, there is a write after read dependency because xj plus 1 is being written in 1, 0 and xj plus 1 is being read in 0, 0. So there are all three kinds of dependencies between elements I, j and I plus 1, j. So j is the same, but I has incremented by 1, and so that's represented by these red edges, which are all write after write, read after write, and write after read, and these are basically these vertical chains. Now, as soon as I have a figure like this, which is totally completely connected, I already know that synchronization-free parallelism is not possible. Recall that for synchronization-free parallelism, I was interested in finding chains or islands of iteration points that are not connected to not data dependent on other parts. So basically the idea in synchronization-free parallelism is to basically take these connected components and put them on different processors, because these connected across components there are no data dependencies because they are not connected. But here the whole graph seems to be connected, and so synchronization-free parallelism will not be possible, and we're going to come to that again. Now there are third type of dependencies which are coming from the fact that let's look at 0, 1 and 1, 0. So 0, 1 is writing to x, is reading from x1, right? So 0, 1 is reading from x1 because 0, 1 means j equals 1, and so that's basically reading from x1. 1, 0 is writing to x1. So clearly, there is a data dependency because they're reading and writing to the same element. And which one is happening later? 1, 0 is happening later in the ascending lexicographic order, and which is actually doing the write. So this is a write after read dependency. So there are write after read dependency from 0, 1 to 1, 0, and similarly from, let's say, 1, 1 to 2, 0, 2, 1 to 3, 0, and so on. And I can basically replicate this in the other sides as well. And so this is basically my dependency graph between the iteration space that we have. And now I'm going to ask the question, is it possible to have synchronization-free parallelism in this particular loop? And the answer is actually no, as I already discussed, because the entire graph, if I take any 2 points in this graph, I will basically be able to find a connecting path between them. And so if there's a connecting path, that means there's data dependency, which means they cannot be arbitrarily reordered with respect to each other. But the next question I'm going to ask is it pipelinable? And so to answer that question, basically what I really need for pipelining is that I need to divide the program into tasks such that the tasks have stages, and there are only one-way dependencies from the first stages of the first task to stages of the second task. Similarly, there are one-way dependencies from stages of the second task to stages of the third task, and so on. Pipelining will not work if there are bidirectional dependency. That means stages of the first task depend on the stages of the second task, or stages of the second task basically depend on the first stages of the first task to complete, and then some stages of the first task depend on some stages of the second task to complete. In that case, basically, I have a lockstep problem because, it's almost like things have to execute in lockstep. First this, then this, then this, then this, then this, and so on between the first and second task itself. But if it's pipelinable, then I can just say, okay, let's first execute the first task and keep signaling the appropriate stages for the second task, and the second task can then execute at its own sweet pace. And that's the wave fronting phenomenon in pipelining. So let's look at this example and try to understand whether this is pipelinable or not. So let's say, in pipelining, the one way to pipeline is basically consider the outer loop iteration as a task and each of the inner loop iterations as the stages. And so basically I want to specialize on the stages. So CPU 0 will basically execute the stage 0 of task 0, which means I, j equals 0, 0. Similarly, stage 0 of task 1, which means I, j equals 1, 0. Similarly, 2, 0, 3, 0, 4, 0. And this is, when I'm writing it in this way, I'm basically saying I, j. And so this would be the pipelining, this is one pipelining scheme, and this is similar to the pipelining scheme that we had seen in our first example in our previous lecture module. However, now let's look at, so these are basically these points that are connected using these vertical chains. So 0, 0, 1, 0, 2, 0, 3, 0, 4, 0. And I'm basically intending that all these points basically execute on CPU 0. Similarly, I can say that all the points at 0, 1, 1, 1, 2, 1, 3, 1, etc. execute on CPU 1. But now if I look at dependencies, then 0, 0 has a dependency on 0, 1 because of this this edge here, this yellow edge here. Similarly, 0, 0 has a dependency on 0, 1 because of this green edge here. Then 0, 1 has a dependency on 1, 0 because of this yellow edge here. So there are bidirectional dependencies between these tasks. 0, 0 is dependent on 0, 1 because of read after write, and 1, 0 is dependent on 0, 1. So sorry, 0, 1 is dependent on 0, 0 because of the read after write, and 1, 0 is dependent on 0, 1 because of this yellow edge, which is the write after read. And I can kind of keep doing this. And whenever I have a picture like this is not a pipelining picture. A pipelining picture should have had only one unidirectional edges from stages in the CPU 0 to stages in the CPU 1. So that you have the wave fronting example. So it seems like as it stands now, this is not pipelinable. So basically the problem once again is, graphically speaking, is that basically I'm dividing the tasks into these vertical strands, but once I do that, then the different stages within each task have dependencies on the other task, or stages on the other task, but they are bidirectional dependencies. As we have already seen, the dependencies are both ways, and that's not something that works with pipelining. For pipelining, I require only one-way dependencies from tasks that are executing earlier to tasks that are executing later. The question now is, can I change this program, for example, by changing the axes of this iteration? Why do I need to basically consider outer loop to be I and inner loop to be J? Maybe I can skew the axes, maybe I can switch the axes, interchange the axes and so on, and maybe after I do that, then the loop becomes pipelinable. And actually the answer is going to be yes. If I change the axes of this program, then the program becomes pipelinable, in the sense that the outer loop iterations basically can be used as tasks which have one-way dependencies on the other tasks. And to see that, I'm not going to show you the exact mathematical answer of how to change the axes, but I'm going to build an intuition in this particular lecture module, and we're going to see the full solution in the next few lecture modules. So if I, for example, divide the tasks diagonally, for example, task 0 is basically just this point 0, 0. Task 1 is 0, 1 and 1, 0. Task 2 is 0, 2, 1, 1 and 2, 0 and so on. So if I divide these outer tasks in this way, then what I see is that between any two tasks, there are only one-way dependencies. Okay, so if I look at the dependencies between the task 0, 0 and the task that has 0, 1, then there are only edges going in one direction, from 0, 0 to 0, 1, from 0, 0 to 1, 0. And so on, right? And so there are only, similarly, if I look at this task which has 0, 1 and 1, 0, and if I look at the other task which is 0, 2, 1, 1 and 2, 0, I will see that the edges are only going in one direction, from this task which is the 0, 1 task to this task which is the 0, 2 task. And so this is exactly the picture I need for pipelining. And so if I can basically change the axes in this way, then I can basically pipeline based on the outer loop, using the outer loop iterations as tasks and the inner loop iterations as stages.